We're going to begin our exploration into sequences and series, and specifically we're going to look at arithmetic sequences and geometric sequences in upcoming sections. But first, let's just talk about in general what a sequence and what a series is. Fundamentally, a sequence can be thought of as an ordered list of numbers. So in that ordered list, the numbers that you include are usually called terms. So let's give an example of a very basic sequence. How about 1, 2, 3, 4, and then ... which means and so on. This is an ellipses. It just indicates that the sequence that I've given is just going to continue in that order. This is going to be the sequence of the natural numbers, which also can be thought of as the set of positive integers. So in this sequence, we talk about where the number is in position of the sequence. So this number right here is the first number in the sequence, so we usually notate it as a sub 1. So with a with a little subscript of a 1, and we would read this as a sub 1. So the second number in the sequence then is a sub 2. The third number in the sequence is a sub 3, and so on for all of the numbers in the sequence. If we want to talk about a general term in the sequence, we can write that as a sub n. So a sub n, and as a reminder, this is going to be in the subscript. This is one specific term in the sequence. We can also put that inside of braces. We would verbally still say this as a sub n, but in this case, because of the braces, we are referring to the entire sequence. So I'm not just looking at one specific term, I'm looking at the entire sequence. So in this example, if I wanted to talk about what's happening in the sequence explicitly, I could write a sub n is equal to n. N is going to be your set of allowable inputs. And this kind of ties us into the maybe a more formal definition of what a sequence is. So a sequence can be considered a function whose domain is the set of positive integers. And the set of positive integers means that you can input 1, 2, 3, and so on. So remember, the idea about domain is this is your set of allowable inputs. So when we start looking at a sequence then, the first allowable input we're going to have is 1, and then we're allowed to input 2, and so on. So if I come back down here to this example right here, the first input I'm allowed to input for n is 1. And what this expression is telling me is that the output is going to match whatever the input in. So if I put in a 1, I'm going to get out a 1. If I put in a 2, I'm going to get out a 2. If I put in a 3, I'm going to get out a 3, and so on. So just to highlight, what does it mean when I say that the a sub n inside of the braces represents the entire sequence? If this is going to be my sequence that I'm looking at all of these numbers, right? Not just one specific term. We've looked at functions previously, but maybe let's compare what we were doing in the past to what we're looking at now. So in the past, we would look at, for instance, a function like f of x is equal to 1 over x, where the domain is x is greater than 0. Because this is a function, it will have a corresponding graph. So here's the graph of this function up here. In order to graph it, what that would look like is we would start finding values in our domain, in our set of allowable inputs. We would put that value into the function. We would get the corresponding output, or the y-coordinate. We generate a set of ordered pairs and we plot them. Once we have enough ordered pairs that we can see what the trend looked like, we would then connect those points either in a line or in a smooth curve. These types of graphs are referred to as continuous because they're all connected, and even though these might be the ordered pairs that we plotted in order to build this graph, because of the line that we've drawn, it also works under the assumption that if I have an ordered pair that I don't have a specific dot on, but for instance like right here, that ordered pair is still a solution to this function. So I can grab values that are not integer inputs, and I would also then have a corresponding output. So I'm not just restricted to the integer inputs. I could put in whatever numbers I want. We just normally don't pick decimals or fractions for an input because they're a little bit messier to work with. But the key thing on these ones is if I wanted to put that as an input, I could. The new thing we're looking at right now is when you put something into your expression, the input must be a positive integer. When you go to graph that, then you're going to get just a sequence of points. We are not going to connect those points with a line or a curve. So those types of graphs are going to be called a discrete graph. So when we're dealing with these sequences, we're going to have, some new notation that we're going to have to get comfortable with. So let's take a look at a couple of examples, just getting more familiar with this notation. So in these next examples, we're going to write down the first 5 terms of the following sequence, and then we're going to graph it. In this first example, my sequence, a sub n, is going to be equal to n squared over 2n plus 1. What I'm going to do to generate these first 5 terms is we're going to start with our first allowable input, which is a sub 1. And what that means is inside of the expression over here, everywhere I see an n, I'm going to put in a 1 instead. So I would end up with 1 squared over 2 times 1 plus 1, which would be 1 over, that's going to be 2 plus 1, or 3. So the first term in my sequence is going to be 1/3. A sub 2, I'm going to put 2 in where I see the n, so I'm going to get 2 squared over 2 times 2 plus 1, which should give me 4/5. A sub 3 is going to be 3 squared over 2 times 3 plus 1. So that's going to give me 9/7. A sub 4 is going to be 4 squared over 2 times 4 plus 1. So that's going to be 16 over, let's see, 8 plus 1 is 9. And then finally, a sub 5 is going to be 5 squared over 2 times 5 plus 1, which is 25/11. Now I could keep going in this manner, but they just told me to find the first 5 terms of the sequence, so I'm going to stop right here. Now it is fine to leave your work like this, but just to show you a different representation, I could say then the sequence a sub n, which is equal to this expression, is going to be equal to 1/3, comma, 4/5, comma, 9/7, comma, 16/9, comma, 25/11, comma, and then dot, 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 meaning and so on. So I can write the sequence out as an ordered list, just putting commas in between the elements. Now the next thing they wanted us to do was to graph it. And in order to graph it, I've got some improper fractions here, so maybe we're going to get the decimal equivalents just to help us with the graphing. 9/7 is roughly about 1.3. 16/9 is roughly about 1.8, and 25/11 is roughly about 2.3. So I can go ahead and graph these. Now for my inputs, where we would have along this horizontal axis, I only need numbers 1 or bigger. Okay, so I don't have to worry about any negative inputs. For my outputs, looking at this, my outputs span from 1/3 to about 2.3. So for my outputs, I'm going to maybe just go up to 3. My horizontal axis, my input variable, is going to be n. And my output axis, which we would normally use the variable y, I'm going to use a sub n. Right? That's going to be the sequence value I get depending on where I am in the sequence. So let's put down a couple tick marks. So on the n axis, we'll go through 1 through 5, and then on my output axis, we'll go from, 0 to 3? So let's plot some values. So if I input 1, the first term in my sequence, my output is 1/3. If I input 2, the second term in my sequence is 4/5. Input 3, the output is about 1.3. Input 4, the output is about 1.8. And input 5, the output is about 2.3. Right, and we're just going to leave it like that. Don't connect these points, because these are the only points that should exist on that graph. All right, very good. So there's our first example, just getting comfortable with the notation and what's going on when we go to graph it. Let's take a look at this next example. So for this one, my sequence b sub n is going to be equal to -1 to the nth power times 2n. So we're going to do the same thing where we're going to find the first 5 terms and then we are going to graph it. So the first thing I'm allowed to input into my sequence is going to be 1. And that's one of the benefits of using this notation with the sequence with the braces, is it lets me know I'm looking at a sequence, so then I know that my set of allowable inputs are going to be those positive integers. All right, so here we go. Everywhere I see an n in my expression, I'm going to put in whatever this subscript value is. So my first term is going to be -1 to the first power times 2 times 1. So -1 to the first power is going to be -1. -1 times 2 is -2. b sub 2 is going to be -1 squared times 2 times 2. So -1 squared is going to be +1 times 4 is +4. b sub 3 is -1 cubed times 2 times 3, so that's going to be -6. b sub 4 is -1 to the 4th power times 2 times 4, so that's going to be +8. And b sub 5 is -1 to the 5th power times 2 times 5, that's going to give me -10. Now there is something very special that's happening inside this sequence. We actually call this type of sequence as an alternating sequence, because the sign on the terms alternates from negative to positive, or it could have started at a positive and gone to a negative. But the key thing is the sign alternates from term to term. So we have this alternating sequence. Let's go ahead and graph it. So on my input axis, which is again going to be denoted n, that's going to be my inputs. So I've only found the outputs for the first 5 terms. So I'm going to have inputs for 1 through 5. My outputs are going to span, it looks like they're going to go from +8 to -10. So I'll put down a couple tick marks. So let's go ahead and plot these. So my input was 1, my output was -2. My input of being 2, my output was +4. My input of 3, output is -6. Input of 4, output of +8. And input of 5, output of -10. So that ends up being the graph for this alternating sequence, and then again, don't connect those points. So in these ones, the sequence was given to us explicitly, kind of like by an expression where I could compute all of the outputs. What we're going to do next then is we're going to give you the sequence, and we want you to come up with the general form for how to generate any term in the sequence. Now remember, we're trying to relate the position in the sequence to the output. So because of that, I find it helpful to write maybe down underneath each term where it is in the sequence. So here's our first example: 1/2, 1/4, 1/8, 1/16, and so on. The 1/2 would be my first term in the sequence. So underneath it, maybe I'll write a sub 1, or more generally, n equals 1. 1/4 would represent a sub 2. 1/8 is a sub 3, and then 1/16 is a sub 4. I'm trying to come out with a general rule to generate a sub n, just a general term in the sequence. Sometimes when they're given these types of fraction problems, it's helpful to look at what's happening in the numerator separately than what's happening in the denominator. Sometimes there's different patterns that's being represented. Here you're also trying to draw on just maybe your number facts. So maybe your addition tables, multiplication tables, exponent tables, those types of things. We're just trying to find some sort of a pattern that's being suggested by our sequence. And then hopefully they've also given us enough terms of the sequence that a pattern is evident. So sometimes these problems might take a little bit of time to figure out the pattern, and that's okay. But since we're also just starting with these, some of the patterns should maybe kind of jump out at us. So don't try to maybe overanalyze it too much. The key thing is to have that good number sense to be able to kind of figure out what's happening in these numbers. So in this example, the first thing I very clearly see is the numerator is always 1. So in my general term right here, I would expect to have a numerator of 1 again. All right, so the key thing on this one is to look at what's happening in the denominator. So in the denominator, I'm going from 2 to 4 to 8 to 16. Now the first thing that might jump out at you is, hey, to get from one denominator to the next, I'm multiplying by 2. But multiplying by 2 every time is the same thing as introducing a power of 2. So this 2 right here can be thought of as 2 to the first power. The 4 is 2 squared. The 8 is 2 cubed. The 16 is 2 to the fourth power. So what's happening in the denominators looks like I'm just raising the exponent on a 2 every time. So I'm thinking then for my general nth term, is this going to be 2 to the nth power? Because it seems like whatever exponent I raise to the 2, that exponent matches whatever index I was on. Or maybe to phrase it another way, where I was in the sequence. So if I was on the third term, I raised 2 to the third power, and so on. Now when we come up with these expressions, it's a good idea to check them in a couple of them just to make sure it works out. So for the check, kind of ignore what you were given so far and just ask yourself, hey, if I wanted to compute the first term, if I was given this sequence, what would the first term look like? Well, it would look like 1 over 2 to the first power, which would be 1/2. So now come back to your sequence. Was your first term in your sequence 1/2? Yes, it was. So if you want, you can check more than just one term. I usually like to check the first term and then one other term. If you wanted, you could check the second term, just to show you could check any of them. I'm going to check what the third term should be. So the third term, if this is my rule, the third term would be 1 over 2 cubed, which would be 1 over 8. Now I'm going to come back up to my sequence. Was the third term in my sequence 8? And I come over here, or sorry, was the third term in my sequence 1/8? And I can come over here and say, yes, it was. All right, so this looks like this is going to work out, and it's going to generate the sequence of terms. Let's take a look at this next example. So the sequence is 5, 7, 9, 11, and so on. Now looking at those, you might say, okay, so I'm jumping from one odd integer to the next, and the first odd integer I'm starting with is going to be 5. So if the first integer I generate is 5, that would be my a sub 1, 7 would be my a sub 2, 9 is my a sub 3, 11 would be my a sub 4, and so on. So I have to come up with some sort of rule that says generate the odd integers, but start with the odd integer 5. So there's a couple different ways that we could generate the expression. One of the things that stands out to me is saying, okay, so in my subscripts, obviously I'm going to go up by 1 every time, right? I'm going to go from 1 to 2 to 3 to 4 and so on. So that's how much my inputs are going up. My outputs are going up by 2 every time. So we can almost think about this as almost being like a slope. But as opposed to slope being the change in y over the change in x, maybe I think about this as being the change in my sequence value, which is denoted a sub n, over the change in the n value, which is where I am in the sequence, that input value. Because this looks like the outputs are changing by a constant value of 2 every time the inputs are changing by a constant value of 1. And that's really what all slope is. It's telling us it's a constant rate of change. So this is making me think this might be kind of a structure of a linear function, which is normally written as mx plus b, right? But in this case, my slope is going to be 2. My input variable is n. And I have to think about what that plus b value would be. Because at this point in time, if I kind of wanted to start running a check, right, if I start with n being 1, the way this expression is written right now, if I just leave it as a sub n is equal to 2n, this would mean my output value, a sub 1, would be 2 times 1 or 2. Well, that doesn't connect with what I was given, right? In the sequence I was given, the output value was 5. So how do I adjust this so the output value is 5 instead of 2? Well, let's not overthink it. Maybe we just need to add the difference, which is 3. So maybe my general expression is 2n plus 3. Now let's check that with a different input. Maybe I start with the third term. So if my third term then, I would get a sub 3 is equal to 2 times 3 plus 3, which would be 6 plus 3, or 9. So was the third term in the sequence I was given 9? If I come back over here, yes it was. So it seems then this expression an is equal to 2n plus 3 will generate these terms. Another idea kind of relating to slope that I saw a student do once, which I thought was a really interesting connection, is they saw that there is this constant increase in the terms as the index, or the point you were in the sequence, went up by 1. So they still saw the slope was being like a value of 2, but they thought about an input-output relationship. They created an ordered pair where they said if I input 1, I get an output of 5. Now you could do that with any term in the sequence, they just happen to do it with that first term. So if I almost think about this as being my point, and I think about the 2 being my slope, we could use a version of point-slope form in order to get something that relates what's going on. Now again, we can only do this because the assumed relationship is linear, right? The output increases at a constant rate as the input increases at a constant rate. So if I think about using like a point-slope form, in this case, if I rewrite it in terms of my variables, I would get, instead of y minus y1 is equal to m parentheses x minus x1, it would be a sub n minus, now my y1 is my point value, so that would be 5, is equal to my slope, which in this case is 2. My input variable is not x, it's n, and then minus the input value on that point, which is 1. If I clean this up, we get a sub n minus 5 is equal to 2n minus 2. Add 5 to both sides, we get a sub n is equal to 2n plus 3, and that's the same expression we came up with. So it was just a slightly different way of thinking about it that I thought was really cool and I wanted to share. Okay, next example. So the sequence we're going to be given is 2, -4, 6, -8, 10. So one of the things that's standing out to me right away is that this is an alternating sequence. When we have an alternating sequence, we're going to have to deal with, or include rather, a -n to an exponent in order to get the signs to start alternating. So maybe to start off with, I might try -1 to just the nth power to build that alternating sign. Looking at my terms, where my first term is 2, my second term is 4, my third term is 6, just looking at the number of the term, not the sign. 2, 4, 6, 8, 10. That looks like I'm building the set of even integers. So even integers are formed by doing 2 times n, where n is going to be the position in the sequence. So if I think this might be my expression, let's go ahead and check it. right, so we're thinking that this might be our general expression for a sub n. Let's check it. So if n was equal to 1, I would get a sub 1 is equal to negative 1 to the first power times 2 times 1. Negative 1 to the first power is negative 1. 2 times 1 is 2. Negative 1 times 2 is negative 2. Was the first term in my sequence negative 2? No, it was not. All right, so this doesn't seem to be working. I got the right number, but the wrong sign. So what we can do then to adjust the sign is I'll have negative 1 to the n plus 1 times 2n. Maybe that's the formula that generates each of these terms. So let's check that. So the first term then, looking at this structure, a sub 1 would be negative 1 to the 1 plus 1 times 2 times 1. So I'm going to get negative 1 squared times 2. So negative 1 squared is positive 1. Positive 1 times 2 is 2. Now I have the right number and the right sign. Yay! I always like to check another one just to make sure everything looks good. So maybe I'll try a sub 3. So a sub 3, based upon this rule right here, would be negative 1 to the 3 plus 1 times 2 times 3. So this would be negative 1 to the 4th power times 6. Negative 1 to the 4th power is 1. 1 times 6 is 6. Is my third term positive 6? It is. All right, so that looks like it might work. Now, this is not unique sometimes when you come up with these expressions. So just to show you another way that you could have written this, you could have written the formula for the nth term is negative 1 to the n minus 1 times 2n, and it would also generate this sequence. Okay, so sometimes there's more than one way to generate this formula for the nth term. Okay, so we've done examples going back and forth. Given the sequence, generate the terms, and then given the terms, generate what we think the sequence looks like. The next concept we're going to talk about is factorials. So as long as you're dealing with an integer that is greater than or equal to 0, you can put a factorial symbol on it by writing the number and then writing an exclamation point behind it. And we would read this as n factorial. Now the factorial is not telling us to say the number really loud or anything like that. It's not to shout it. What it is, it's telling us a math operation. So if I have 0 factorial, that's going to be defined as equal to 1, and 1 factorial is also defined to equal 1. For any integer greater than or equal to 2, how we figure out its factorial is you're going to multiply that integer and then multiply by every integer less than it going down to 1. So let's take a look at a specific example. I think that's going to help make this a little bit more sense. Let's say I need to find 5 factorial. So what I'm going to do is I'm going to start with the integer I'm given, which is 5, and I'm going to multiply that by every integer less than 5, counting down by 1 until I get to the number 1. So that looks like 5 times 4 times 3 times 2 times 1. So factorials will tend to get really big really fast, so having your calculator handy might be helpful. This one isn't too bad because this is going to be 5 times 4, that's 20, 3 times 2 is 6, and then 20 times 6 is 120. So this one isn't too terrible just to compute by hand. Most scientific and graphing calculators will have a factorial option in there where you can just key in what this number is supposed to be right here, and then you can just grab the factorial option. So you should find where that is on your calculator. If I want to compute 6 factorial, now we could do 6 times 5 times 4 times 3 times 2 times 1, but I'm looking at this as my next example because I want you to see that I could compute 6 factorial as doing 6 times 5 factorial, right? Because the 5 times 4 times 3 times 2 times 1 is the same thing as 5 factorial. So the nice thing about factorials is if you know how big the term is for this factorial, the 5 factorial, we just need to multiply that output by 6. meaning I could just do 6 times 120 since I've already computed 5 factorial over here. So 6 times 120 is going to be 720. This becomes a helpful fact when working with more advanced sequences later on, that if I want to compute n factorial, I can break this apart as computing n times n minus 1 factorial. So this comes in handy to simplify some stuff, because it says if I want to compute a certain factorial, if I know what the value of the factorial is in front of it, I just need to multiply it by whatever this extra number is. Being able to compute the next one by knowing what the value is of the previous one in front of it is a big idea. It actually leads to a whole class of sequences that can be defined as what's being called a recursive formula. So I can define a sequence by assigning a value to the first or the first few terms, and then I can specify what the nth term is by a formula that will involve those preceding terms. So let's take a look at an example to kind of clarify what that is all talking about. So let's write down the first 5 terms of the recursively defined sequence where a sub 1 is equal to 5 and a sub n is equal to 2 times a sub n minus 1. Okay, so sometimes that first value that's being given to us is called the seed, because it's going to lay the groundwork for everything to come after that. Okay, so if I want to find the first 5 terms, the first term is being given to me, so we're just going to say thank you and use that. The second term, a sub 2, is going to be found by doing 2 times a sub 2 minus 1. Remember that all I'm going to do here is, for whatever this subscript is, I'm going to put that into my kind of general structure right here. So a sub 2 would equal 2 times a sub 2 minus 1. Well, a sub 2 minus 1, that's 2 minus 1 is equal to 1. So this is telling me that the second term is equal to 2 times a sub 1. Well, I know what a sub 1 is. We were given that. So that's going to be 2 times 5, which is 10. So here's where we can see in order to generate the second term, I needed to know what the term in front of it was. That's what our recursive formula tells us. So if I want to generate a sub 3 is going to be 2 times a sub 3 minus 1, or 2 times a sub 3 minus 1 is 2. So a sub 2, that's what I have right here. That's 10. So a sub 3 is going to be equal to 2 times 10, or 20. What my recursive formula is telling me that if I want to generate any term, is going to be 2 times the output that preceded it. So a sub 4 is going to be 2 times a sub 3. Well, a sub 3 was 20. So 2 times 20 is 40. A sub 5 is equal to 2 times what I got for a sub 4. Well, a sub 4 was 40. So 2 times 40 is 80. So those are going to be the first 5 terms of the sequence. When talking about a recursively defined sequence, I feel like I would be remiss if I didn't talk to you about a very famous example of a recursive sequence, which is called the Fibonacci sequence. Maybe you've heard of it before, but if you haven't, I absolutely need to introduce this to you because this is one of my favorite ideas. So for the Fibonacci sequence, what this is it's defined as f1 is equal to 1 and f2 is equal to 1. All right, so these are going to be my seed values. Then to get any general term, f sub n, it's going to be equal to f sub n minus 1 plus f sub n minus 2. Now there is a lot of notation in there, but we're going to break it down. So what this is telling me then is if I wanted to find f sub 3 is equal to f sub 3 minus 1, or 2, plus f sub 3 minus 2, or 1. So to generate any term, what I'm going to do is I'm going to add the previous two terms. So f sub 2 is 1, f sub 1 is 1, and 1 plus 1 is 2. So the third term in my sequence is 2. F sub 4 is going to equal f sub 4 minus 1, which is 3, plus f sub 4 minus 2, which is 2. F sub 3 is 2. F sub 2 is 1. And 2 plus 1 is 3. So the third term in my, the fourth term in my sequence is 3. So to more generally write this out, what the sequence is going to look like is 1, 1, 2, 3. The next term is going to be the sum of the previous two terms, so 3 plus 2 is 5. The next term is the sum of the previous two terms, so 3 plus 5 is 8. The next term is going to be 5 plus 8, which is 13, and so on. And this sequence is known as the Fibonacci sequence, and it pops up in all sorts of cool places, especially for a lot of stuff that occurs in nature. Alright, so next big idea is to talk about summation notation. So the sum of a number of terms in a sequence is called a series. A series can be finite, which just means it ends at some point. So I'm going to sum a bunch of stuff, so maybe like 1 plus 2 plus 3 plus 4. Maybe I stop there. That would be a finite series. Or it can be infinite. So an example of an infinite series would be 1 plus 2 plus 3 plus 4 plus and so on. So I don't stop anywhere. I'm just going to keep adding forever. If I want to add a bunch of terms, and on our first examples we're going to look at the finite series, the ones that end at some point. Infinite series are a little bit more difficult to work with, and we'll get there eventually, not in this section. So let's assume that you have a finite series, which means you're going to add a bunch of stuff up and you're going to have a last number that you want to add up. Okay, so this would be then the first number that you want to add up, a sub 1, and a sub n is going to be whatever that last number is that you want to add up. So we're going to use this special notation. Okay, this symbol that we're seeing right here, that kind of looks like a sideways M, this is a Greek letter, capital Greek letter, and it's sigma. And all this Greek letter is used to represent is it means to find the sum. Add up a bunch of stuff. Okay, so this letter right here means add up a bunch of stuff. Over here, this is telling us the sequence that I want you to add. And then notice that we're just going to shift the variable that we're using over here. Now we've changed it to, there's a k and also an n. So k is your index. Okay. And the index will tell us where to start adding in our sequence, and often we will have k is equal to 1. Okay, that's often what we'll see, but you don't have to always start at 1. You could start at some general number, and we'll look at an example of that. So I could start at putting 1 into my expression, and then it tells us where to end. So sometimes this part right here is called the lower index because it tells us where to start. And then this whatever value up here is where we end. That's called the upper index. Before we look at some specific examples, let's look at a very general example just to start trying to wrap our head a little bit more around what's going on here. All right, so let's say that I have my sequence being 1, 2, 3, 4. And that's it. My sequence just ends at 4. For that sequence, I could find its series. And the series is, I'm just going to take the terms in my sequence, but I'm going to add them up. Okay, so this would be the associated series for this sequence. 1 plus 2 plus 3 plus 4. Okay, and so if I add them all up, then I would get 10. That 10 is referred to as either the sum or the summation for this series. If I wanted to write this in my specialized notation, if I referred to as my sequence more generally, right? So if I wanted to, for instance, keep going, my sequence could be denoted as a sub n is equal to n. We talked about that earlier. So in this case, if this was my sequence and I just wanted to add up the first 4 terms, how I could write that using my special sigma is I would write that symbol. At the bottom, I would write k is equal to, and I would tell you where I want you to start adding. So I want you to start adding at the first term. At the top, I would tell you where I want you to stop adding. So I want you to go up to the 4th term. And then over here, I would write what the sequence is that I want you to add up. So I could either write a sub n, or I could give you the expression for what that sequence is. And in this case, I'm just going to write what that sequence is right here, which would be, that would be k. So this is saying start at k equals 1. So first put a 1 in for k. Then you're going to put a 2 in for k. You're going to put a 3 in for k. You're going to put a 4 in for k. And then I've reached my upper index and I'm going to stop. So I have just generated that series. Right, so new notation, anytime we reach new notation, it's good to do a couple of examples. So let's take a look at a couple more examples. So this one I want to find the sum from k equals 1 to 5. Okay, so maybe we'll write that down in our notes. How do we say this? So we would say this as the sum of k equals 1 to 5 of, and then I would cite what my expression is that I want to ultimately sum. So this in this case would be k squared. All right, so here we go. So first we have to figure out what the terms are of the sequence, and then once we find what the terms of the sequence are, we can add them all up to get our series. So the first term in our sequence would be 1 squared. So I'm just going to put 1 in for k. And then this is telling me take my input and square it. I'll clean that up on my next step. The second term, if k is equal to 2, that would be 2 squared. The third term, if k equals 3, would be 3 squared. The fourth term would be 4 squared, and then the fifth term would be 5 squared. I'm going to stop because I have reached my upper index. Right? So this is telling me where I need to stop putting in my input values, go no further. So let's clean up each one of these expressions and add them up. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. This isn't too terrible just to type it into your calculator, add them all up, verify, you get 55. So that is going to be the sum that I get from that series. Now in that example, I was able to calculate a very specific sum because I was given a very specific value to go to. We can also talk about these sums in more general terms. So notice for example B, this is going to be the sum of k equals 1 to n of k over k plus 1. Now for this one, I'm not going to be able to compute the actual sum because I wasn't given a value to go to, I was given a general variable to go to. So this one we're just kind of expand out kind of what each term looks like, and then we're just going to leave it like that. So we're going to start at putting 1 in for k. So again, everywhere I see the k, I'm going to start stepping up by this index value starting with 1. So my first term is going to be 1 over 1 plus 1. My second term is going to be 2 over 2 plus 1. My third term is going to be 3 over 3 plus 1. My fourth term is going to be 4 over 4 plus 1. And that's enough. Now let's go, so plus dot dot dot, and now we're going to write our nth term. So that just means everywhere I see a k, I'm going to write n. So that might feel a little weird, but yeah, we are just going to write, instead of one variable, we're going to put a different one in there. This is the variable of the upper index of the summation. So to represent our final sum then, we're just going to go ahead and clean some of these expressions up. So this is going to be 1 over 2 plus 2 over 3 plus 3 over 4 plus, now maybe I don't even need this term. They didn't tell me how many terms to start with, so maybe I'll just give 3 terms. It's kind of common for these to give maybe the first 3 terms and then the last one. The last term would be n over n plus 1. If you would want to write, you know, the plus the 4/5 in there, it wouldn't be wrong, but sometimes we just stop after giving 3 or 4 terms, assuming that we've given enough that we think someone can figure out what the pattern is. Okay, so let's do one last one, and maybe for this one you get to try it on your own and see what you get, and then compare it to what I'm about to write. So the summation we're going to do is the sum from k equals 0 to n of k squared minus 1. So notice on this one it's telling me to start my sequence inputting 0 as the first value. Okay, so I encourage you to take a moment, try to figure out if you can figure out what each terms are, starting putting 0 in for k, and then add them all up through to what you would get if you put n in for k, and maybe give the first, let's say 4 terms, and then the last term. Okay, so here we go. So hopefully you've done this on your own, paused it, tried it, and then let's compare if we got the same thing. So if I put 0 in for k, you would get 0 squared minus 1, or 0 minus 1, which would be negative 1. Plus. The next step up would be 1. So 1 squared minus 1 would be 1 minus 1, or 0. Plus. If I put k is equal to, so this was what I get if I put k is equal to 1, sorry, 0. That's the first one. K is equal to 1. Next one is going to be k is equal to 2. So I would get 2 squared minus 1, or 4 minus 1, which is 3. If I put 3 in for k, I get 3 squared minus 1, or 9 minus 1, which is 8. And I think that's enough. Now we can just write down your nth term, so that'll be what you just give if you put n in for k, so it'll be n squared minus 1. So here would be your series. And we can't really do much more with that. I mean, we could add up the numbers that we see, but normally we leave it in this expanded form so we can very clearly see what that sequence value is that I'm adding up. And normally on these it's very important to be able to verify the first term in the sequence, the second term in the sequence, and so on. So we just leave those out all expanded. We don't try to combine those and simplify those. Okay, very good. Now let's go the other way. So on the previous examples, we gave you the summation notation and we wanted you to expand out the sum. Now on these ones, we're going to give you the expanded sum and we want you to write it in the summation notation. Okay, so this is going to tie in your pattern recognition abilities to come up with like that general nth term for the pattern. Except keep in mind on these ones, we're writing everything in terms of k. So looking at these, I have 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, plus 1 over 5 squared. So inside the parentheses, it looks like I already have 1 over, and for these numbers, if I started my counting for my value for k at 1, the denominator would always be where I am in the sequence. So it looks like then my general expression would be 1 over k, and then squared. And it looks like I'm going to keep going. So I'm going to end my sum at k is equal to 5. So that is going to be what it goes up here, okay, on top of my sigma notation. Now one comment to make on this is when you go to write this for the summation notation, don't write 1 over k and then squared and not put the parentheses around that. All right, this would be bad. In this notation, that square really only affects the 1. It wouldn't affect the whole thing. So if you want that square to affect the whole thing, you've got to put parentheses around the whole thing. The alternate answer that I would accept on this would be if you had your sum from k is equal to, well, got to put a 1 down here, k is equal to 1 to 5. If you wrote it as 1 over k squared and you specifically put that squared on the k value, okay, that would also generate the sequence, although I think on this one, this would be kind of the more acceptable version, is having the parentheses around the whole thing, just because that's the structure that they gave to me, so I might as well mimic it. But definitely don't not have the parentheses on there if you're going to put the squared around that whole thing. Right, that's a bad way to write it. All right, let's take a look at our next example. So it's 1 plus 3 plus 5 plus ... plus 2n minus 1. Now this one is going to be really helpful because they're already letting us know kind of what that general expression is for that nth term. So all I really need to do to put this thing in summation notation, okay, so this is going to start then at, so my general expression is going to be 2k minus 1. I'm thinking I'm probably going to be starting k at 1, but again, it's a good idea to check. If I put k is equal to 1 in here, do I get this term out? So if k is equal to 1, we would get 2 times 1 minus 1, or 2 minus 1, which is 1. Is that my first term? Yes. Okay, so you need to kind of check that because we've already seen on a previous example, sometimes they like to throw it for a loop and have k be 0 or something like that. So we just want to make sure we start at 1. That's usually what's going to happen, but again, we should double check as opposed to just assuming. So we're going to start at putting 1 in for k and generate these terms, and we're going to go all the way up to the nth term. So this one is just going to have a general number up there at the top of the sigma. For this expression inside right here, this 2k minus 1, we must put that inside parentheses. Do not write this as 2k minus 1 and omit the parentheses. No, 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 you can't write it like that. If you were to write this without the parentheses, a summation is really tricky. It's about as tricky as an exponent. So you know how an exponent can only connect what's to its immediate lower left? Well, the sigma notation can only connect to what is to its immediate right. So if you write the sum or sigma and then right after it you have 2k minus 1, this really means that the sigma only attaches to the 2. So like if you have your lower index and your upper index here. So this is then going to only say sum 2 a whole bunch of times from the first term to the nth term. Once you get that sum, multiply that sum by k and then subtract 1 from the whole thing. Okay, so that's very much not what was happening in this sequence. Okay, so this doesn't make any sense. The parentheses absolutely need to be there, so that way I know that I need to compute that entire expression in order to generate one term. So rule of thumb is just get in the habit that put parentheses around whatever that expression is that you're going to be taking the sum of, right? It's always better to have it and not need it than need it and not have it. So some properties of sequences. So when we're doing these sums, you know, of our sequences, when we're basically forming a series, we want to know what we are and are not allowed to do when we're forming these sums. So when we're adding a bunch of terms in a sequence, what can we do? All right, so let's say that my sequence is c times a sub k. So if we look at the expanded form of that, you're going to have c times the first term plus c times the second term all the way to c times the last term. Since every term involves a c, we could factor it out. Now c is just going to be a real number, so it's going to be a constant. So we can factor that out in just sum of the terms that we would get by adjusting this expression right here, this a sub k. So that's one of the things that we are allowed to do. Another thing that we are allowed to do is that if we are going to take the sum of, and we have two different sequences here, so if we have the sum of two sequences, we can break it up. and we can just find the sum of the first sequence, the sum of the second sequence, and then add those two values together at the end. If we're going to take the difference of two sequences and then want to sum up all of those differences, what we are allowed to do is we are allowed to also break that up. We could find the sum of the first sequence, the sum of the second sequence, and then just subtract those two sums. And then one of the last things that we can do that's really helpful is if I'm trying to find the sum of a sequence from 1 to n, what we can do is we can break this up and find the sum from 1 to j, where j is going to be some number that's less than n, and then the sum from j plus 1 to n, and add all those up. Now this one has a lot more letters floating around on there, so let's break it out what's happening, all right? The first term would be a sub 1, the second term would be a sub 2, the third term is a sub 3, and so on and so forth. So what we're saying is we're going to go to some arbitrary number in the sequence, which we're going to call j. The next term would be a sub j plus 1. Right? The next one would be a sub j plus 2, and then blah, blah, blah. And we would keep going until we hit the nth term. If I'm trying to find this sum, and I want to add up all of these guys, what this rule is telling me is if I'm trying to add from the first term to the last term and I'm trying to find that entire sum, what I could instead do is I could find the sum from the first term to some arbitrary term in the middle. I could find that guy's sum. And then I would sum from the term right after that through the end. I would find that guy's sum, and then I would add those ones up. And that would give me the sum of the whole thing. Now, we normally don't necessarily use it in this form. We would use this most commonly when we're trying to find the sum and where we're going to start is not going to be at 1. So let me give you an example. Right? Let's say I want to find, so let's say my general expression would be k is equal to from 1 to let's say 20, and let's say my a sub k is, I don't know, k squared, whatever. Okay, what I could do then is I could find this from 1 to some arbitrary number, let's say 5, and then my next one would start at, so if this one is going to go from 1 to 5, the next one would start at 6, and then I could go through the end. So where this is helpful is this is maybe what I would be given. They want me to find the sum from k is equal to 6 through 20 of k squared. So if this is what I'm being asked to find, what we could then do, okay, so if this is what I'm being asked to find, the sum from k is equal to 6 through 20 of k squared, using this property, what we could do is, okay, I could find the sum from k is equal from 1 to 20 of k squared, and then just subtract off the terms that I didn't want to sum. So if I wanted to sum from 6 to 20, apparently the ones that I don't want are the ones from 1 to 5, and I could subtract those off at the end. That's more commonly how we're going to use this property. Now, if that still feels like a lot, that's okay. We'll work through an example so you can kind of see how this is all going to play out. For these different properties that we looked at, one of the properties that's not on this list that I want to highlight is that if you have the sum from k is equal to 1 through n of ak times bk, so if you're multiplying two sequences and then you're going to add up all of those terms, this is not equal to the sum of ak from k is equal to 1 through n times the sum of bk from k is equal to 1 through n. So We can break it up over adding, we could break it up over subtracting. You're not allowed to break it up over multiplying. So just be careful about what rules you're applying. You can't make up new ones. They're not going to work. So now that we've talked about what we can do with different types of series and how we can break things apart, the other thing that we are very interested in, what the actual sum is. And normally we don't want to sit there and have to type in all of the numbers in our calculators from the first term to the last term. So there's going to be some useful formulas for us depending on what the sequence looks like, and then the corresponding series it generates, what sorts of sums that we're going to get. So the first one we're going to look at is if k is equal to 1 through n of c, where c is, this is just a constant. So this would be a number that you can see, which is going to be equivalent to adding c to itself n times. Well, that's going to be equivalent to doing c times n. If I'm doing the sum of k is equal to 1 through n of k, okay, so that's just going to generate for me the sequence 1, 2, 3 through n, and I want to add up all of those terms. That's going to be equivalent to computing n times n minus 1 all divided by 2, where n is that value at the upper end that I'm trying to go through. If I'm looking at the series from k is equal to from 1 through n of k squared, okay, so this is going to be taking the square of all of my positive integers through n squared. Well, that's going to be equivalent to n times n plus 1 times 2n plus 1 all over 6. And then finally the sum from k is equal to 1 through n of k cubed, which is going to be summing all the cubed positive integers. That's going to be equivalent to n times n plus 1 all over 2, and then that whole thing squared. So to wrap up this section, let's go ahead and apply some of those formulas defining the sums of various sequences. So remember, the sum of a sequence, this whole thing is just called a series. Right? And then ultimately the answer we get from the series is called the sum. In our first example, we're going to have the sum from k is equal to 1 through 5 of the expression 3k. In this expression, what we're going to be able to do is we're going to be able to pull the 3 out in front or outside of our summation. And we can do that because it's a constant. It doesn't involve my variable k. What that's going to look like is I'm going to have 3 times, and so then I'm going to have the sum from k is equal to 1 of 5 of just k. Now how that's going to help me is I have a formula that tells me if I am finding the sum from k is equal to 1 through n of k. Okay, so k would just be like this. This is just going to generate for me the sequence of integers. This is equivalent to doing n times n plus 1 divided by 2, where n is whatever value I'm summing through. So in this particular problem, my value for n would be 5. So using that formula then, for this sum, I would get 5 times 5 plus 1 all over 2. So that is to clean that up. So this is going to give me 3 times, that's going to be 5 times 6 over 2. Or 3 times, let's see, 5 times 6 is 30, 30 divided by 2 is 15, so 3 times 15 is 45. So instead of doing this long ways by finding each of the terms of your sequence and adding them up, you can just use this formula. Now this one, because your n value is 5, that wouldn't necessarily be too terrible for you to just do it by hand, but let's say for instance I had that upper index being 20. Do you really want to sit there and figure out 20 terms in a sequence and then add them all up? Maybe you're like, okay, well that's not too bad. All right, what if I change this value up here in the upper index to 100? Do you want to find 100 terms in that sequence and add those up? So at some point in time, it gets to the point where these formulas are going to be time savers for us. So we definitely want to use them. All right, in our next example, we are going to have the sum from k is equal to 1 through 10 of k squared minus 4. Now, this one I wanted to show you just because the typesetting is a little bit different. In this case, this is not going to have the k is equal to 1 kind of below that sigma symbol, and then the 10 being kind of resting above it. It has those values off to the side. This sometimes occurs in typesetting, just so that way this expression can fit on one like line inside of, like a program or when you're typing things out. So just if you see the upper index and the lower index off to the side of the sigma notation, I still want you to be comfortable knowing how to read it. In your own work, you can write it either way. I tend to try to write it at the top and the bottom just because I like that notation a little bit more. Okay, so the expression that we're going to find here is k squared minus 4. We have a property that tells me when I'm subtracting two sequences, I can break this up into individual sums. So I can find the sum from k is equal to 1 through 10 of k squared, and then I can subtract the sum from k is equal to 1 through 10 of 4. I have formulas to help me with both of these. So we have a formula that says if you're trying to sum from k is equal to 1 through 10, or rather n, talk about this more generally, through some number n of k squared, that is going to be equivalent to n times n plus 1 times 2n plus 1 all over 6. I strongly encourage you to write these formulas in your work when you're using them, especially as we're just starting to learn them. It'll help you get more comfortable with what they are saying that we're allowed to do. Okay, so let me just expand out what this first sum is going to give me. So my upper index is 10. So this formula says do 10 times 10 plus 1 times 2 times 10 plus 1 all over 6. And I'll clean that up on my next step. I just wanted to write out what that formula gives me. Now this next one looks a little bit weird because I don't see a variable in here, right? So it's kind of like, what do I do with this? So this is saying go from k is equal to 1 through 10 of 4. So on this one, if I were to like expand this out, we have a formula for this, but sometimes the formula, people forget what they are allowed to do because this is actually our most simple case. So it's almost like too simple because they're like, I don't see a variable here. Well, this is basically saying that there's no input as k varies. So if k is equal to 1, you want your expression to be 4. If k is equal to 2, you want your expression to be 4. If k is equal to 3, you want your expression to be 4. And we're going to do this until we get k is equal to 10. I still want my expression to be 4. So I'm adding up a whole bunch of 4s. Specifically, how many 4s I'm adding up? There's going to be 10 of them. So the formula for this, just to kind of go back to understanding what that formula is telling me, that if I'm going to sum from k is equal to 1 through n of c, where c is just a constant, well, that's going to be equivalent to doing c times n. So for this particular expression then, this is going to be equivalent to doing, well, in this problem my c is 4, so that's going to be 4 times, and then my value for n is going to be 10. So that's what I get on the second part of this summation. Okay, so I'm just going to clean this up a little bit before I go to pop this into my calculator. Up here in the numerator, I'm going to get 10 times 11 times, that's going to be 2 times 10 plus 1, so that's 21, over 6, minus 4 times 10 is 40. I'm feeling the need to clean up that numerator before I enter this whole thing in my calculator, so 10 times 11 times 21, that part alone just gives me 2310. 2310 over 6 minus 40. Now I'm just going to enter that whole thing in my calculator, feeling a little bit more comfortable with how to type all that in, and you should get 345. So that's going to be the sum of this series. Alright, so we're going to see how these formulas are helping us kind of break down the different parts of our expressions and get these various sums. In the last example, we are going to be summing. Now this is where that one formula is going to come in really handy. We're going to be summing from k is equal to 6 through 20 of 4k squared. So notice that we're not starting at 1 On this one, we're starting at 6. All right, and a lot of our formulas, if you look back at the different formulas that we have, they all start at k being 1. But we have that one special formula that allows us kind of adjust where we're starting. So let's see how to apply it. The first thing on this one is this 4, I'm going to pull it out in front. So I don't have to have the constant in here. I can pull the constant out in front, and I still have the sum from k is equal to 6 of 20 of k squared. Now I have a formula for summing k squared, but my formula needs k to start at 1, not 6. So there's a couple different ways that we could adjust that, but using kind of the formula approach, what we're going to do is we're going to figure out, first off, what would it be if I started at 1 through 20 of k squared. So we're going to sum kind of the entire series, which will include some values I don't want, right? If I just want from, so if 1, 2, 3, 4, 5, 6, 7 out through 20, this is who I want to sum, right? The summation I've written right now is going to sum the whole thing. It's going to sum from 1 through 20. No, I don't want all of those guys, right? So let's subtract off what I don't want. I don't want these ones, right? We want to subtract those ones out. So we'll subtract out k is equal to 1 through 5 of k squared. Okay. And the cool thing about this is notice now that both of my new expressions both have a starting value of 1, so now I'm going to be able to use my formula. Now an important thing of this is that this 4 needs to affect all of this. All right, so I'm going to put a big brace around all of this that says compute all of that stuff first, figure out what I get when I do this difference, and then multiply 4 by all of it. Okay. So what's going on here, just to kind of summarize, is that we wanted the sum from 6 to 20. So what we're going to do then is we're going to find the sum from 1 to 20, and we're going to subtract off the sum from 1 to 5. So if I pull off the sum from 1 through 5, this is going to leave me all of the terms that I do want to add up. And I have some cool formulas then that will get me each one of these pieces. All right, so I have my k squared formula written right here, so I'm just going to go ahead and use that and start putting in some values. So on the first piece right here, my value for n is 20. So I would have 20 times 20 plus 1, or 21, times 2 times 20 plus 1. So that's going to be 40 plus 1, or 41, all over 6, minus, right, on the second summation I'm trying to do, my value for n is going to be 5. So I'm going to have 5 times 5 plus 1, which is 6, times 2 times 5 plus 1, which is 11, all over 6 again. Now there's a couple of different ways that you could finish cleaning this up. I'm just going to multiply out these numerators. So the 20 times 21 times 41 is going to give me 17,220 all over 6. My second fraction, the 5 times 6 times 11 is going to give me 330 all over 6. These two expressions already have common denominators, so I'm just going to put them together and just say thank you for that. So I get 16,890 over 6, and at this point in time I'm just going to pop this into my calculator, and we get 11,260 is my sum. Alright, so that concludes looking at sequences and series. So lots of new notation, lots of new variables floating around, new formulas, new rules. Expect for these to take some practice, ask lots of questions, and after you get comfortable with just generally how to working with sequences and generally how to working with series, then we're going to get into some more specific cases, specifically arithmetic sequences and geometric sequences.